and analysis, we can know the real models is a candidate to depict the complex anomalous diffusion process. From different forms of the equation, we can know that different forms of variable equations can depict the different diffusion process. But I should say that because these real models they just proposed in the 2001, so the mathematical foundations of this model is still immature. Here the classifications of real models, properly speaking, is not strict because we can say this is the functions of the derivative orders. This function can also be only constant the time, so it's not strict. Just from the reason why, what's the reason cause the derivative order models? Next, we will make the link between the variable order models to CTRWs, because here we use the variable order models of time derivative and space derivative. So next, we will have a try in the CTRW models, use the variable waiting time PDF and the variable jump length PDF to see the behavior of the CTRWs.
Can you put back a slide? Is this already being done or you want to do?
I want to do this. I have done this part, the variable order models in the time derivative. These three parts will be done in the future. The second models I will introduce the distributed order models. We can see the form. The difference lies in this term. It has the integral. This is discrete form. You can see here is the intriguing behavior of this model is that we can get the multiple laws here. So this model.
In the multi-power law, you should have a coefficient, do you?
Coefficient?
The multi-power law in front of the t should have a coefficient of c sub k or something.
Oh yes. Yeah.
Otherwise, you just put 1. No, it doesn't look right to me. Okay.
So we can build the relations between multi-order models and multiple laws. So it's a very intriguing topic. In this model, we should say that the DO model is still belong to the consistent order models. In the theoretical, we can prove that in the long-term behavior, it can depict the decelerating or accelerating diffusion process. So the third model, we will propose the random order models. Why we propose these models? Because in some systems, it is interfered by some noise in diffusion process, such as the oscillating external field or unstable system parameters. So those noise will cause the system fluctuation. So we will investigate the behavior of the system under the noise. So here is some examples. This is diffusion in this caused by current. We can see the variations with the time had fluctuations. And also in these papers, at the tails, had fluctuation. So we want to propose this model to depict this process. This is expressions of the R models. The expressions in Fourier Laplace domain, we can get the expression like this. So, from this expression...
Wait. How do you do a Laplace transform?
I know you'll get stuck here.
You have a time dependence on the epsilon sub t. How do you do that?
Because according to papers by Hitalis, in this the transform here t is a depart to 2 time scales. This t is a time scale, and this is another time scale. So they can do the Laplace transform in 2 time scales. So we can say in these expressions, this t can transform into s, but this is still the same.
But then you ought to do a real multi-time scale expansion of the equation and parameterize the time difference. If you have one long, slow variation and one fast, short variation, then you ought to explicitly look at where's the connection term, rather than saying that they're independent, because they're not independent of one another.
I gave the same critique. So I don't know what's the best way to resolve this, but this is possibly mathematically incorrect shortcut.
Yes.
Need more justification. Okay.